Good morning or good afternoon, depending on where you are. My name is Kathy Kroll. I'm the co-director of technology transfer for the IBT ABC UTC at Florida International University. I'd like to welcome you and approximately 1,400 other registrants for our 177th webinar in our monthly webinar series. Today's featured presentation is the next generation of prestressed precast concrete deck beam bridges. Mike Como, CHA's Chief Bridge Engineer, will be presenting. We will start with a few announcements and then move into the presentation that will last approximately 40 minutes. The presentation will be followed by a question and answer session. First, I would like to announce our 2026 World Bridge Engineering Conference that is coordinated by the IBT ABC UTC that will be held in Miami, Florida, December 1st through the 2nd of 2026. This conference is co-sponsored by the US DOT and over 32 state DOTs. We're currently accepting abstract submissions. The deadline is March 20th, 2026. For additional information on all things related to the conference, please see our website and/or use the QR codes that are on the screen. In addition to abstract submissions, we're also accepting award nomination submissions for Innovative Bridge Engineer of the Year, Innovative Bridge Owner Agency of the Year, and project awards for both ABC and IBT in the categories on the screen. Again, see our website and/or use the QR codes for additional information and submissions. Next, I'd like to thank the U.S. Department of Transportation and its University Transportation Program that sponsors the IBT ABC UTC. The University Transportation Centers Program has been in existence since 1987 with the mandate to help address our nation's ever-growing need to maintain and enhance our transportation system. The IBT ABC UTC at Florida International University and our partner universities are focused on accelerated bridge construction and innovative bridge technologies. We'd like to express our appreciation to US DOT and their UTC program for supporting the IBT ABC UTC so that we can continue to serve the bridge engineering community with events like this webinar series. Before we move on to today's webinar, I'd like to share some announcements. We typically share events 3 to 4 months in advance, but since it is December and the time of year I put together my calendar for the coming year, I thought it might be helpful to others to share 2026 events of note. There are quite a few, so I'll point out that a PDF of these slides are included in the download section of the GoToWebinar dashboard. You can download it for future reference. The first event of 2026 is the Transportation Research Board's 2026 annual meeting in Washington, D.C. from January 11th through the 15th. Registration is open. Next is the 2026 PCI convention at the Precast show. It will be held February 2nd through the 6th in Kansas City, Missouri. Registration is open. The AISC NSBA's 2026 Steel Bridge Conference will be held April 22nd through the 24th in Atlanta, Georgia. Registration opens in January. The 4th International Interactive Symposium on UHPC will be held in Des Moines, Iowa, June 14th through the 17th. I've had the privilege of attending the first of these conferences, so I can attest to the quality and the value of the conference. Add it to your calendar. AASHTO's Committee on Bridges and Structures annual meeting will be June 28th through July 2nd in Charlotte, North Carolina. The Engineer Society of Western Pennsylvania will be presenting the International Bridge Conference, the IBC, from July 15th through the 17th in National Harbor, Maryland. The IBT ABC UTC will be holding our annual in-depth web training on September 8th, 2026. This event is similar to these monthly webinars, but it has a 4-hour time slot so we can dive deeper into the topics. While the topic has yet to be finalized, our current direction is to provide topics on accelerated and innovative bridge deck preservation. If you have ideas for this event, please send me an email. PCI's Committee Days Conference will be September 9th through the 12th in San Antonio, Texas. The Composites and Advanced Materials Expo, CAMEX, will be September 21st to the 24th in Atlanta, Georgia. Next, the American Segmental Bridge Institute, ASBE, will be holding their annual convention from November 8th to the 12th in San Antonio, Texas. The year's finale, of course, will be our biannual World Engineering Conference from December 1st through the 2nd in Miami, Florida. I started with the information on this, so you can look at it for additional information at the beginning of this presentation. If you know of other events of note, please send me an email so I can track and coordinate around them. So on to our upcoming webinar events. Our next monthly webinar will be in the new year on June 22nd from 1 to 2:15 Eastern. The presentation will be Minnesota DOT Innovates, Modernizing Bridge Management with Digital Twins and Artificial Intelligence. We will welcome Ed Lutgen and Jennifer Wells from Minnesota DOT and Barrett Lovelace from Collins Engineers. Registration is open. You can sign up now on the IBT ABC UTC website. Also in January, on the 30th, we will hold our next quarterly research seminar from 1 to 2:15 Eastern. The featured project will be predicting key bridge characteristics using machine learning. Our colleagues from University of Washington will be presenting. Mark your calendars. That's all for our announcements. On to our standard housekeeping items. As many of you may know, these webinars are recorded and posted on the IBT ABC UTC website in the section titled Monthly Webinar Archives. So you can access this and all previous webinars for future learning and to share with interested colleagues. I'd also like to point out that a PDF version of today's presentation is provided in the GoTo dashboard on the right side of your screen. You can download these PDFs during the training session. They will also be posted in the archives. Lastly, this presentation will be followed by approximately 15 minutes of question and answer. With that, we will begin our featured presentation. We are happy to welcome Mike Como from CHA Consulting back to present. I think that this is the 11th time that you've presented for webinars for this series. Does that sound about right?
That sounds about right. That does sound about right, yes.
Yeah, so we greatly appreciate your contributions to the industry and your willingness to share your time and expertise. So with that, again, welcome, Mike, and we'll turn screen controls over to you.
Well, it's my pleasure to be here today to talk about a subject of a lot of interest to a lot of people, judging by the number of people that have registered and also just the interest we're seeing in this. We're going to talk about the next generation pre-stressed precast concrete deck beam bridges. And deck beams are beams that act as a structural deck supporting wheel loads as opposed to a composite beam with a composite deck on top. A little bit different. On the screen is what we're going to talk about today. One version of the deck beams that we're going to talk about today. To make it clear, the white boxes are the beams, and then the gray areas between the beams are connections between the beams, which is the big topic that we'll talk about today. They really make up this next generation of concrete deck beam bridges. I've been doing bridge engineering for 42 years now. I think every year of my career, I've been involved in some way or another dealing with pre-stressed precast concrete deck beams. So this is the next generation, we call it, a new idea that is starting to take hold. So the objectives for today is to become familiar with this new product, learn why we developed this product, and I say we because it was done by a committee. There are a few limitations, we'll talk about that. Then we're going to talk about how to design and detail one of these bridges. You should be able to walk away from this pre-station today with the ability to actually design and detail one of these in your state. And lastly, we're going to spend quite a bit of time talking about how to connect these deck beams, which is the primary innovation in these beams compared to previous versions of precast deck beams. So what I'm going to present today, I'm here on behalf of the PCI Northeast Bridge Technical Committee. This is a committee that's been around since 1980. Alex Bardo, the state bridge engineer from Massachusetts, was the first member. I think I came on 6 months later, around 1980. So do the math, 35 years we've been meeting. A very robust committee, and the key thing is the membership of this committee is not just industry, it's actually the majority of members of the committee are DOT bridge engineers. So it's very much a DOT-oriented committee, and we develop practical solutions to bridges using precast, pre-stressed concrete. There are some PCI staff members, but an important part also is the producers. The precast producers in the Northeast are available for consultation on this committee, as well as academia and a handful of consultants. We've been doing all kinds of documents. I can have a whole presentation on what we've done over the years, including the New England Bulk T, Northeast Bulk T, I should say, full depth precast deck panels, ABC, precast substructures, and next beams are all items that came out of this committee. Shown on the right is the current membership of the committee. that worked on this particular document we'll talk about today. So we're here to talk about adjacent box beam bridges without topping slabs. That's the key thing about today's. And in my 42-year career of designing bridges, we have a love-hate relationship with adjacent box beams and slab bridges. We love them because they're very thin. They give you a very thin superstructure, and if you've got issues with waterway clearance or roadway clearance, it's a great solution for that. They go together quickly, fast construction, that's a great thing. However, there have historically been issues. The hate part of this is we've had issues with the joints, with leakage through the joints causing deterioration. The photo on the right shows a bridge. I'm not sure where this bridge is, but it's showing that leakage through that joint, the third joint in, has caused deterioration of the beams, broken strands, and stuff we don't want to see. So we have historically seen leaking through joints, which has made these things problematic. And we're looking for a better solution for this as we move forward. This is a slide that covers potential causes of joint failures. I've actually read in my career probably 15 research papers on these bridges and these joints. My theory is we design these bridges as a one-way slab. We have 20, 25, even 30 strands in each beam running lengthwise. And traditionally, the way we connect these things is with a handful of post-tensioning strands and maybe some rods, some threaded rods in the transverse direction. Reality, though, it's not a one-way slab. It behaves like a two-way slab, primarily because of just the width of the bridge and also the fact that we have stiff edge beams with the parapets cast on top. And I'll cover in a slide, the next slide, exactly how I think that behavior affects the joints. AASHTO has recommendations for connecting these beams together. In this section of Article 46221, which is livelihood distribution factors, it shows this diagram, cross-section G, and you see the PT on there, and it says basically transverse post-tensioning shown for some cross-sections are intended to make the units act together. Then it says a minimum of 250 PSI pre-stress is recommended. Now, recommended is a key word. It's not mandatory, but it's recommended. So if you take a 6-inch deep shear key and you do the math real quick, you find out you need 18 kips per foot of bridge. We typically use a fraction of this value. So we're not really connecting these details based on the recommendations in AASHTO for the transverse post-tensioning. I mean, the reality is I've seen research papers saying that we need 3 strands every 3 feet, the whole length of the bridge, which is really unrealistic in most cases. So my theory about why these joints fail, and there are different opinions out there and different theories, but it's just what I've seen over the years, is that, again, it's going to act as a two-way slab. You put a load in the middle of the bridge, so you have a truck in the middle of the bridge. We all know the center beams are going to deflect more than the fascia beams. That's just common understanding of structural behavior. But we have a stiff edge beam, especially with a parapet, that is not going to deflect this much. And what that results in is a deflected shape in cross-section, what I'm showing on the screen here. And you look at that deflected shape and you can see at the outside portions of the beam, you have negative bending across the joints. And in the middle of the bridge, you have positive bending. Well, the negative bending has the potential to open up those joints. And what I've seen over the years is that first interior joint is usually the first one that starts leaking. So the behavior that we've seen in these bridges seems to defend this particular theory that I have. Again, I've read research papers that back this up as well. And as I said before, the research has shown the amount of transverse pre-stressing required is significant. And I don't know anybody who's actually putting that much pre-stress in these bridges because it's just not economical. There has been recent research done at the University of Cincinnati talking about thermal gradients that could cause joint failure. I don't disagree with that research either. I think it's part of the problem, but maybe not all of the problem. So what have we done in the past to solve this problem? Many states are now adding a composite topping slab above these beams to solve the problems, essentially make it act like a composite I-girder or girder bridge. It does improve durability. It definitely solves some of these problems. But the issues with this approach is it does thicken the structure. We're losing some of that structural efficiency on the thickness of the structure for vertical clearance underneath. It does add cost, and it's significant. We're adding a lot of concrete. We're adding a lot of reinforcing steel. So you're adding cost to the bridge, making it thicker. And then the last bullet, I have seen on several locations around the Northeast especially, where we're starting to see reflective cracking through the joints, even with the topping slab. So it was a better solution than what we previously did. But I'm not 100% convinced it is the final solution. So nothing against this detail. A lot of states use it, and it seems to work well, but we're starting to see some cracks showing up with these joints. So with that, our PCI Northeast Bridge Tech Committee decided to come up with a solution, and I'll give credit where credit is due. The Vermont Agency of Transportation was the first state to come up with this idea. The idea was to take advantage of recent research on deck level connections, stuff that came out of the ABC world, And if you're familiar with the next beams, and the next D beam, where the top flange of the D beam is the actual structural deck, and we have details to connect the top flanges with hook bars and reinforced concrete closure joints. Our goal is to take those details and marry them together into a slab bridge as shown on the bottom of the screen. And our goal is to emulate, that's a word we use a lot in the world of prefabrication, we're emulating a solid slab bridge. And what's really nice about that is it's covered very well in the AASHTO LRFD bridge design specifications. There are provisions for how to design a solid slab, cast in place concrete solid slab bridge. Our goal is to emulate the solid slab bridge with a precast option with precast members that are connected. So shown on the right side of the screen, PCI Northeast, we issued these recommended guide details. These details literally were published. The final publishing is happening this week. We included it in the handout in the chat box for this webinar. You can also go to www.pcine.org to download these documents. So what do they look like? These beams are similar to a box beam or a slab that you've used for many years, with one big exception. It's got bars projecting out of the side of the beam that are similar to a next D beam closure joint. We're lapping these hook bars. The photo in the center is a little bit off. The beams aren't quite close enough together, but we have lapped bars, and we fill that joint with concrete. We could also use ultra high performance concrete as well. The photo on the left shows the fabrication of one of these beams in the plant. This is from JP Carrera in Vermont. And the photo on the right is a bridge, I believe in Woodstock, Vermont, one of the first bridges built by Vermont Agency of Transportation. So as far as span ranges, this table shows for typical products that we use. For the adjacent slabs, which are shallow pre-stressed beams, typically span up to about 50 feet. Box beams can span anywhere from 30 to almost 100, even a little over 100 feet. Next beams are in the range of 40 to 80 feet. Bulb Ts can handle spans 70 on up to well over 120 feet. These deck beams, though, we're looking at the family of deck beams that were developed will cover anything from 0 to very short span up to 100 feet. So it's a really wide range in the short span bridge market. So these bridges are very much applicable to many, many short span bridges across the US. As far as structure depth goes, generally structure depth is going to be similar to a box beam or a composites or a deck beam with a composite slab topping. Will be thinner than that because we're eliminating that topping slab and going to just a simple deck beam with the vehicles driving right on top of the beams. So here's the key features. The key sides of these beams have full depth shear keys, and we have reinforcing projecting out the side of the beam to make these connections. There's a significant amount of reinforcing. We're looking at number 5 bars spaced at 6 inches is typically used. We are recommending only straight strand because while we can drape strands in these beams, it just complicates fabrication. And in most cases with the bonding, we come up with a very similar design anyway. Here's a key feature of the last bullet is these do not require custom forms. Any fabricator with a standard forming bed for building girders can make this. The only difference is that they have to fabricate new side forms, and I'll show some pictures of that in a minute. So we came up with 3 different types of deck beams for the committee, for short spans, medium spans, and if you want to go with spread beams to accommodate, say, utilities. So the first, we call them solid deck beams. Now the word deck is in every one of these options we show, again, because we're driving directly on top of the beams without a topping slab. So solid deck beams are relatively short spans up to about 55 feet. We're looking at beam depths of 12 to 21 inches. We're recommending no voids in the beams to save money in fabrication, and to at these kind of spans, it doesn't save an awful lot to have voids in these beams. We have 2 different details for connecting the beams. We have hook bars with cast in place concrete, and we also can use straight bars with UHBC, and they're shown in the 2 details to the right. The real difference between traditional slab beams is that the connecting bar is projecting from the sides. As a committee, we decided to vary the width of these beams from 47.5 inches down to 35.5 inches. Don't get too riled up about the half-inch increments. That's a Northeast thing. Some states go 48 to 36, but the reality is these would work for any width that your fabricators in your region are familiar with producing. The next one up, we went to box beams now. We originally developed a solid deck beam, spans up to about 55 feet. We wanted to push it further, so we came up with very similar details to connect box beams. And they're very similar details. The connections are similar, just deeper. And again, they differ from traditional box beams because we have the projecting bars coming out the side of the beam. Again, we're varying the beam widths from 47.5 to 36.5 in 4-inch increments, and we're varying the depth from 24 to 42 inches beam depth in 4-inch increments. I should say 3-inch increments. Technically, if your local fabricators can go deeper than 42, you can go deeper with these as well. It's just that's what we typically see in the Northeast. The last one are spread box beams. A lot of states like using spread boxes. What's nice about them is they can handle utilities and maybe a more cost-effective solution because you're using fewer beams in a cross section. And we'll cover these details as well. And you can see the dimensional variation is similar to the previous box beam details. So how do you fabricate these things? Well, the key is that you have to have custom side forms. And what's shown in the photo is from J.P. Carrera in Vermont, some of the earlier, the first bridges built. They're using wood side forms. They want to, and we all want to go to metal side forms so we can reduce costs. But until these become more standardized and more commonly used, they're using wood side forms. The key thing is you see the lower left photo shows the slots, vertical slots in the side form. You have to be able to slide that form off after the concrete cures, and you need those vertical slots to get that hook bar out, to get the side form around the hook bar. There's an issue though, how do you keep the concrete from going out of the slots between the two hooks? And the answer is the shear key shape is a secondary piece in the form that covers up those holes. It's very important to understand how this thing gets built because the shape of the shear key and the location of those bars coming out of the side of the beam are very much work together. The bars have to be just above and just below the shear key, and I'll show that in a bit why that's important. Another thing we developed as a committee is a cross-section geometry. What's nice about these beams, as opposed to traditional box beams, where you're married to the width of the box beam setting the width of the bridge. So say if you have 48-inch box beams and you're stuck in a 4-foot increment as far as the width of the bridge. With these beams, we can vary the width of the beam, as I mentioned before, but we can also vary the width of the joint. The details we've developed work for different width joints. So you can actually dial in an exact bridge width. So we created this little spreadsheet. In minutes, you can go in and figure out, well, I want to use a reinforced concrete joint with hook bars, and I can go in and quickly enter the total width of the bridge, and within minutes come up with a beam width and a joint width that works to develop that exact cross section. Live load distribution is something we always need to figure out, like how do we design these beams? And this is where the AASHTO LRFD bridge specs come into play. AASHTO Article 4623 is the equivalent strip width method for determining the lane width, the portion of a slab bridge that resists the bending moments due to trucks and the shear due to trucks. It's cross-section A in that article. And it's based on the assumption that these beams are properly connected with distribution reinforcement that will emulate a slab-type bridge. So the key thing is we can very simply calculate that dimension E, and dimension E is the AASHTO calculation of the strip width, where the load, that portion of the bridge is resisting the loads. And then we know the beam spacing, and we take the beam spacing divided by E, and we come up with a live load distribution factor, which is the percentage of the lane that is supported by each beam. Very simple calculation. As far as fascia beams go, we have a similar equation for fascia beams, looking at E divided, or X divided by E. So distribution factors, we've created a spreadsheet, and very simple. This is not complicated math. The AASHTO provisions are very straightforward for these types of bridges. And we have a nice little spreadsheet that'll calculate distribution factors for multiple lanes loaded and single lane loaded. So PCI Northeast, we developed recommended guide details. We developed these for a lot of the products that we develop in our committee. We notice we're not saying the word standards. These are not considered standards, although they are very close to standards. But the reason we don't call them standards is because each state can make minor revisions to these if they want. We try to get states to have all the same details. That's our goal as a committee, but minor changes are definitely allowed. And so we have a nice little weasel word paragraph that basically says, these are not standards. You have to do your engineering, and we're not responsible for everything. But again, these things are very close to standards, but they are not standards. And they were published literally this week. So now we're going to spend the next portion of the presentation to go through these guide detail sheets. And I'm not going to go into a lot of detail because there's a lot of information on these sheets, but I'll hit the high points, and you have copies of these and you can download and you can review them at your leisure. But I'm going to just hit the high points. The first several sheets are frequently asked question sheets. They look like this, and we have 3 sheets of FAQs, and they're broken up into different categories. The first category is general questions. First defining what are these beams? What is a solid deck beam, box deck beam, and spread box deck beam? Big question, are they proprietary? The answer is no, they're not proprietary. Any PCI producer can produce these things, not a problem. Are they I'll skip over a few of these. Are they more economical than other bridge systems? That's a good question, and we have had a few questions asked about that. We don't have a huge history on cost, But definitely by eliminating the voids and eliminating the topping slab, the reinforced topping slab, we're very confident that these will be more cost effective than building a box beam bridge with a topping slab. I'll talk about utilities. There's two options. You hang utilities on the outside of the bridge, or if you have a sidewalk, you can spread the boxes underneath the sidewalk and have utilities there as well. And as far as bearings, any bearing configuration you currently use for box beam bridges would be applicable to these as well. Some questions on bridge geometry. We'll talk a little bit later about maximum span lengths. I'll cover that in the next slide or two. Can we use them on skewed bridges? Yes, we limit the skew to 45 degrees just for detailing purposes. That you, in theory, can go more than 45 degrees, but historically, it gets a little complicated with detail. Can they be used in a curved bridge? No, these are straight beams like any box beam bridge. You'd have to chord the bridge on the curve. Can you use a variable width? Can you do a variable width bridge? The answer is yes, you can. It can get pricey and get complicated, but you can, in theory, vary the width of the joint across the length of the bridge. In theory, that could be done. Haven't seen it done, but it could be done. I'll talk a little later about profiles, how we handle profiles with these beams. Cross slopes, we typically set these beams on the cross slope of the road. As far as the widths, I mentioned that before, we vary the width from 35.5 to 47.5, and we also vary the width of the joints. So for that reason, we can develop a specific bridge width. We can accommodate just about any bridge width that's out there. And the last question, can multiple beam widths be used in a bridge cross section? We typically discourage this for cost. If you have one odd beam in a cross section, that's a custom fabrication for that one beam, and that price will be high. We have seen, and my firm is actually designing a bridge right now in Massachusetts, we're using two different beam widths in stage construction. In stage one, we have one beam width. In stage two, we have another beam width. It was a very tight location. The stage construction line was pretty well dictated by work offside the bridge, off the bridge. And that's okay because those beams will be fabricated at two different times. But in general, we try to keep all the beams the same. Then we get into design questions on FAQ sheet 2, talking about what software you can use, and really any software they use for pre-stressed design would work. I talked about how to distribute dead load and live load. We talk about how to do that. I mentioned that before. Can I design the beams for continuity? Yes, if you can make a box beam bridge work for continuity, this is the same detail would work here. How do I design the connection between the deck beams and box beams? I'll cover that in later slides, but the answer is AASHTO article 512.2.1, and I'll get to that in a minute. And I think that's good enough. Integral abutments, you can, again, just like continuity, if you have details for integral abutments for box beams, they would work here. And is post-tension required? No, the answer is no post-tensioning is required transversely to connect these beams. Some more FAQs. What options are available for connecting? We'll cover that in the slides. We have some notes about top tension at the beam ends. We seem to have problems with that from time to time, so we have specific requirements for that. Same thing with confinement. Can voids be used in solid deck beams? We don't show them, but yes, if you want to put voids in, you can. It's not a no-no. It's just something we try to do to save money. The next FAQ sheet, we talk about deck and wearing surfaces. Again, there is no deck on top of these, so we talk about that. Talk about the keyways. We use exposed aggregate surfaces on the keyways to control leakage. We do recommend a wearing surface, either concrete or bituminous, more for rideability and profile, is to get these beams to be a smooth surface at the end. A thin overlay is something that we would recommend. In the Northeast, we do use a lot of asphalt overlays with high quality waterproofing membranes. Railings, there was a question was submitted on railings. Any detail that you currently use for adjacent box beams or adjacent slabs would be applicable to these bridges as well. And then the rest of this I'll cover in the detail sheets. So on the first detail sheet, we have general notes and design guidelines. We basically say you have to design the bridge. It's not something that's designed by the fabricator. The engineer of record has to design the bridge, specify strengths, just like we would with any precast beam bridge. As far as cross sections, we have several different options. We have solid deck beams with hook bars. We have solid deck beams with UHPC bars, UHPC joints, I should say, deck beams with hook bars, spread deck beams, and spread deck beams with straight bars. So we have several different options to use that, whatever your desire is for your bridge. This detail is very important. This covers the geometric configuration of each one of the beams. And the key thing is the shear keys. We do not want anyone changing the shear keys. It affects a lot of reinforcing within the beam. And then the one on the bottom is the spread box beam. You'll see the top flange is a little thicker to accommodate the deck section that's cast between the beams. The detail, this note here, just section notes showing these cross sections of the bridge. We're showing the minimum joint widths in these details. You can vary the joint widths to provide an exact cross section. So if you go over here, these are just basically details showing the different types of deck beams that we're using here. So then we get into section properties and span lengths. So this is for solid deck beams. Gives the details showing the cross section that was used, the variable width and variable depth. And the table to the right covers all the beams that we are recommending. And here are the section properties. Reality is anyone with a CAD program can calculate these section properties pretty quickly, but we like to include them for preliminary design information. But here's the big question. Now, in the past with beams, we've actually developed span tables. We decided as a committee to go away from span tables. And the reason why is that typically there's about 20 assumptions that are made when you develop a span table for a beam. And the reality is any particular bridge, probably 5 or 6 of those assumptions are not going to be valid, which means the maximum span length is not going to be valid. So what we have found in the preliminary design of these things is that in general, we can meet the AASHTO LRFD requirements for span depth ratios that are specified in Article 25263. For the solid deck beams, every design we looked at met those requirements. So we can hit the minimum number for AASHTO. So to be conservative, we're recommending using 90% of that value for if you're doing a type study, your first shot at it, use 0.9 times that AASHTO value. Well, we developed a handy little equation. If you take the depth of the beam in inches, you multiply by 2.5, you get a span length in feet, an approximate maximum span length. And for instance, for a 24-inch deep beam, you would get a span of a 60-foot maximum span. Approximate's the key word here. If you really are that close on span structure thickness and during a type study, you may want to run a preliminary design to make sure you can make it work. So then we have section properties for the box deck beams. I won't cover those. Essentially, it's the same information we had on the previous sheet, and then for the spread deck beams as well. Now we'll get into liable distribution factors and some of the details. So in occasion, you may want to mix the beam widths. You may want to have 2 different beam widths in a cross section. So we give guidance for how to calculate the beam width. And the liable distribution factors when you have different beam widths. And essentially what you do is you look at the beam spacing on either side of the beam in question, and you take the maximum of those 2 spacings to calculate the distribution factor for that beam. And remember before, the liable distribution factor was just the beam spacing divided by the strip width E. For spread box beams, a little bit different. AASHTO LRFD Article 4622 does have distribution factors for spread box beams. It's in cross section D in the table. So you would use those equations for liable distribution for spread box beams. Now we're going to talk about roadway profiles. The reality of the world is when we cast a pre-stressed beam, it's going to come out with a camber, a certain camber. I could talk an entire hour, 2 hours on camber and camber issues. But really, the key thing is it's going to come out with a camber. The chances of the roadway profile matching that beam camber are very low. So the reality is we have to make some adjustments to accommodate the roadway profile with the camber of the beams. In this detail here, there are 3 different situations: a tangent profile, crest vertical curve, and a sag vertical curve. One option is to vary the depth of the beam. And some states are okay with this, and fabricators can definitely do this. It does increase the cost a little bit, and it can affect the design a little bit too. So you got to be a little careful, but it can be done. So you essentially cast the beam to match the roadway profile, taking into account the camber that you anticipate. Another option is to keep the beam depth constant, which is shown on the bottom of the screen, option 2, and vary the overlay if you have an overlay. So that is an option that many states use. It's probably the cheapest option, and the engineer would then just calculate the thickness of the overlay based on the design camber. Keep in mind that the parapet or barrier height also varies in height to accommodate the variable overlay thickness. So you have 2 options. The note in the middle is very important. If you decide to keep the beams, vary the depth of the beams, I should say, what we recommend is varying the top portion of the cross section. The portion of the beam above the shear key is what you would vary. You keep the shear key dimensions the same and measure from the bottom, but vary that top dimension. So now we get into the details. This sheet here, I can't tell you how much time was spent on this sheet here to come up with these details, but it's very important. And this shows the reinforcing within the beam. Within the beam, it's standard reinforcing that we use for any box beam bridge or slab bridge. The difference are the bars coming out the side of the beam. And you'll see the bars come out just above and just below the shear key. When we have some interesting dimensions here, the center line of the bar is coming out 2 13/16, 3 7/16. That dimension is based on the number 5 bar, and that's the central line of the bar. It's an exact dimension because that would put the bottom of that bar just above the chamfer, and the top of the bar and the bottom would be just below the chamfer. This facilitates the form removal in the shop. It's very important that we follow this. For the box beams, similar details on the left, very similar details to the slabs, and on the right are showing the spread box beams, which are a little bit different because now we have a reinforced concrete slab section between the beams. We have notes in the reinforcing, and we talk about strands and reinforcing. We're recommending using number 4 bars for shear reinforcing within the beam in most cases. But and we do say minor adjustments to the details, the longitudinal reinforcing and the bars within the beam can be changed to accommodate what state standards are. And as far as the strands go, we recommend straight strands of debonding. We talk about debonding in the articles in the AASHTO LRFD regarding debonding limits. And that's pretty much all shown. The pattern shown depicts the maximum number of strands that are allowed. We're recommending 0.6-inch strand, pretty much like every other beam you design. As far as designing bars, here's one of the big questions we get is, how do we design those hooked bars coming out of the side of the beam? Well, if you look up the AASHTO provisions for slab bridges, Article 512.2.1, if you're doing a cast-in-place concrete slab bridge, one of the requirements are that you have distribution steel. And typically distribution steel are bars that are transverse to the main bars, or I should say the strength bars. I guess the term we use, primary steel, in the bottom of the beam. We have distribution bars. Well, we are emulating a cast-in-place concrete slab. So it makes logical sense that the hook bars coming out of these beams would act as distribution steel if it was a cast-in-place slab bridge. So therefore, we recommend designing those bars, the size of those bars, based on this AASHTO requirement. And typically, in most cases, we come up with number 5 bars at 6 inches work. In a couple cases we've seen, maybe you have to go to number 6 bars, but 5s to 6 work in just about every case we looked at. So for designing those bars, you will size those bars based on this AASHTO provision for distribution steel. And then from there, you could design the connection using details I'll cover in a few minutes. And here we go. These are the details for connecting these beams together. So the key thing is we have a lap splice of the hooked bars shown on the upper left. That's the AASHTO lap length for hooked bars, and that is, it's actual development length for hooked bars. It's what the lap length is. And from once you know the lap length, then you can calculate the width of the joint. There's an equation shown in the middle of the sheet there. And you can come up with the width of the joint and the length of the projecting bar P1 from the side of the beam. These were developed for next D beams, and we're just using the same details again. In the boxes in the middle of the screen, we have standard designs for 4 KSI concrete with number 5 bars, the width of the joint, the bar projection length, and the lap length. And that's the recommended minimum width joint at 13.5 inches. We do recommend a maximum width joint of 18 inches. That number was picked out of thin air. It's just we felt as a committee we don't want to go much more than 18, but you certainly can. And the detail on the right is for UHPC, similar notes, similar details. You can see the width, we can get down to 7 inches for the width. And we recommend a maximum width of 12 inches for those beams. Again, the cost of the UHPC is pretty high. We don't want to go and put an 18-inch wide UHPC joint. If you have a wider joint, we recommend just going with regular reinforced concrete. Back one slide, just to notice, and the spacing of these bars are 6 inches on center. We don't want to mess with that because the side forms have slots at 6 inches, which means we have a non-contact lap splice of 3 inches. This is all consistent with the AASHTO LRFD guide specs for ABC. I won't spend a lot of time on spread boxes, but basically it's a slab section we're casting, very similar details and very similar notes. So as far as designing these closure joints, as I mentioned before, we need to design reinforcement using the AASHTO LRFD guide specs for ABC. That has to do with the lap splice dimension required. And again, the area of the reinforcing bars are consistent with AASHTO Article 512.2.1 for transverse distribution steel and solid cast-in-place slabs. Then we get to the last details now, and we're looking at end block details. If you're familiar with box beams and slabs and the AASHTO provisions for bursting stresses and confinement, you need to provide splitting reinforcing in both the vertical and horizontal planes at the end of the beam. So we have details showing how to achieve that to meet the AASHTO provisions for splitting and confinement. And then skews, recommended details for skewed bridges. I mentioned before, we recommend up to 45 degrees. The key thing is the projecting bars should be kept square. This facilitates form removal. And the other thing is you do not have to carry those bars all the way to the end of the beam. It gets very congested at the ends of these beams. So we recommend stopping short. Once you get to the bearing, there's no need to go beyond that for connecting these beams. Inevitably, there's going to be differential camber between the beams, which is another reason why we like to go with overlays. We have details here showing how to handle differential camber. We recommend a maximum differential camber of 1/2 inch. PCI actually allows more than that, but we recommend that we have a tighter differential camber. And Managing camber is a whole other presentation that I could give, but again, looking at these details, you see the bars coming out just above the shear key and just below the shear key. I can't emphasize that enough, but just showing how we handle variable differential camber across the beams. So in conclusion, the adjacent precast deck beams have had a checkered past. We've seen leakage through joints over the years. It's been problematic. One potential cause is the lack of a significant moment connection between the beams. So our PCI Northeast Bridge Tech Committee is looking to improve on the performance of these beams by improving on that connection. There's 3 types of deck beams that have been developed: slabs, box beams, and spread box beams. All of them have reinforced concrete moment connections between the beams, emulating a cast-in-place concrete slab. And we feel this represents a significant improvement over previous deck beam designs. We've developed guide details and design recommendations, and they're available at www.pcine.org. Don't go to pci.org. That's the main, the PCI national website, pcine.org. And I'd like to thank the committee, our PCI Northeast Bridge Committee, for all their work in developing these sections. So with that, I'll be happy to answer any questions we might have.
Thank you very much, Mike. So usually Paul Lyles does our question and answer, but he's having some technical difficulties. So I am going to start. Hopefully he will join us. Jamal El Kaise is also with us today. He is recently retired from FHWA. All right, so we'll start with the pre-webinar questions. Has a traffic rail been tested while attached to one of the precast concrete beams? If so, how well did it perform?
The answer is no, but as we said before, we're emulating a cast-in-place slab. So if your state has standard details for barriers on solid slab bridges, you can use those. If your state has standard details for adjacent slab or box beam bridges, you can use those as well. So the committee felt there was no need to go to that extreme for barriers because standards already exist for those types of barriers on these types of bridges. So I recommend using whatever state standard you have. And every state does it differently. I know, like in Ohio, they like bolting a railing on the outside of the fascia beam. That's fine. But other states embed anchor rods into the fascia beams as well. So there's different details out there, and they're all applicable.
All right, next question. Were live load deflections taken into account for the design tables?
Yeah, as I mentioned before, we did not develop span tables for this, and that's one of the reasons we didn't, because every state's got different requirements. I shouldn't say every state. There are different requirements in different states for live load deflection. Some states don't consider live load deflections, others use the national recommended values. So again, we're getting away from span tables because I can't tell you how many times, like with next beams, we say, oh, a next 42 whatever can span 68 feet. And then PCI would get a phone call saying, I got a 68-foot bridge and I can't get the beam to work. Well, why? Well, I got a 42-inch concrete barrier. It's really heavy, and I got, the dimensions of the bridge are different. So those 18 to 20 assumptions that we use to develop the table, inevitably 4 or 5 of those are not applicable, which means I can't get to that span length. So we're basically giving some general guidance using that equation I showed, 2.5 times D, and that'll get you in the ballpark. If you're that tight on structure thickness, we do recommend you run your own calculations to see if you can get a certain beam depth to work. It's every time we publish span tables, every time we get phone calls saying I can't make that one work, and it's unfortunate because what will happen is somebody will do a type study, say, okay, this 24-inch beam will work. They get the final design and 24-inch beam doesn't work. Now they got to go to a 27-inch beam, and now all of a sudden they got to raise profile and they start complaining. If you're that tight on clearance, we recommend just do the calculations in your type study, preliminary calculations to see that it can work.
Okay, we had a couple of questions related to post-tensioning and transverse post-tensioning. And I believe that that's really not applicable, but I'll have you explain it better.
One of the goals of this design was to get away from transverse post-tensioning. There are a number of different details out there. Some states use threaded rods. I actually like threaded rods better than transverse PT, but the reality is it hasn't worked. We have had problems with transverse post-tensioning. It doesn't seem to be the right solution. So one of the main reasons we developed this beam was to get away from transverse post-tensioning and go to a more robust reinforced concrete connection.
Okay, we also had a number of questions on durability, and you also covered this in the presentation, but again, if you could elaborate on how you envision the durability of this and how it relates to your current practice.
Yeah, that's a great question. I mean, we are eliminating a slab, so there's no, like, people. One question was asked about, what about deck replacement? Well, there is no deck, so it's like any other adjacent beam bridge that we've designed. where the beam is the actual deck. I've heard cast-in-place concrete slab bridges described as bulletproof. A lot of states, like Ohio, builds lots of cast-in-place concrete slab bridges, and they get very good durability out of these structures. Our goal is just to emulate that with precast concrete and pre-stressed concrete. So the durability should be even better than a cast-in-place option. So what I do recommend, I like using waterproofing membranes and asphalt overlays. I think that's a very durable solution. We've had a 50-year track history in the Northeast doing that. It's the Europeans, that's their standard approach to bridge engineering. But if you want to go with a concrete deck, you want a bare concrete surface, you can go bare concrete. You might have to do some grinding at the top of the beam, and we have some notes about how to handle that. But I want to design the beam with a little extra thickness that you can grind off to get a smooth profile. But the reality is you can do it, or you can go with a concrete topping. Some states have thin concrete overlays they use, and you could use that as well. I mean, you can go with latex concrete. You can actually go with UHPC topping if you want. There's a number of options out there. Yeah, polyester concrete's now becoming more popular. So there's a number of options you have for overlays. Whatever works for you in your state, go for it. I recommend some type of wearing surface. And more than anything, just to deal with the profile issue and to deal with the smoothness issue and the differential camber. It solves a lot of those problems, having some type of overlay on top of the bridge.
Sounds great. One more question. Is specialized heavy equipment needed to construct this system?
Yeah, nothing different than a typical pre-stressed bridge. Your girders has to be erected. That's it. So the answer is no, nothing special. Standard cranes work.
Okay, so Paul, I left off at question number 10, and we can go ahead and kick it over to Jamal as soon as we're done with the pre-webinar questions.
Okay, first one here, number 10. How do you account for the torsions, for the effects of torsion on the distribution of shear between the webs near the support?
As far as I know, in my world, we don't necessarily go through a torsional design for these beams. It's just something we don't do. The reality is, the moment connection we're providing between these beams essentially is going to act, the structure is going to act as a solid slab, so the torsion on individual beams essentially goes away. Yeah, we design these as 2D structures, essentially a two-dimensional design. We don't get into three-dimensional design for box beams. It's an interesting subject, and I think a good research project will come out of that, John, and you can do that. But the answer is we don't typically design box beams for torsion. It's not required in the AASHTO RFD.
Okay, this is a pre-webinar question. It says, what beam types are incorporated in the system? You kind of went over that in your presentation. I don't know if you want to add anything to that.
Yeah, again, we have 3 different beam types. We have thinner slab bridges, then we have box beams, and then we have spread box beams. So we have 3 different types that we developed for these deck beams. The key things, they're all deck beams, where the intent is not to have a composite deck on top of it. The beams act as a structural deck for the bridge, which was the original intent for these beams when they were developed 50 years ago, probably more than 50 years ago. So we're trying to return to original intent for these bridges.
Okay, it says, what are the best practices for how designers should detail the longitudinal joints that result as a product of the precast elements? You kind of showed that, and you stressed very carefully how the keyway had to be. You want to add anything to that?
No, we have very specific details developed for that, and just follow those details. If you want to change the shape of that shear key, it affects a lot within the beam itself. And then originally we had the hook bar on the bottom going below the bottom mat of reinforcing, and some of the details I noticed in the presentation showed the old detail. We moved that to the top of the bottom mat, which affected the size of the shear key. And we felt it was just a better cover. And the concern was there's a lot of congestion at the bottom of the beam with the strands and all that. And it seemed to work better if we just moved the hook bars just above the bottom mat of strands. And that's where the dimensions that we're specifying come from.
Okay. Question was, please comment on the potential for the use of lightweight concrete in the future.
That's another presentation for another day, but I have seen states build lightweight concrete pre-tension girders. You can. There's no reason you couldn't do it here as well. It comes down to states' preference. Some states allow it, some states do not. I'm a big fan of lightweight concrete. There's no reason you couldn't do it here.
Okay. Do you have any studies on the economy of the system over conventional pre-stressed beams?
We haven't built enough bridges to have a really good database of costs. In general, we recommend that the cost of the beams are probably 15 to 20% higher than your traditional box beam without bars coming out the side. there is definitely a cost associated with fabricating these beams with the bars coming out the side. The key thing is our fabricators in our committee have verified that, yeah, we can build this. It's possible to build a beam with the bars. So I'm thinking 15 to 20% more for the actual beam. And then you could price out the concrete going between the beams using standard unit prices that you have in your state. We don't have a lot of data, but when you compare that to the cost of an adjacent slab bridge with a composite deck on top of it, I am convinced it's going to be cheaper. Matter of fact, I gave a presentation in Ohio on the solid slab deck beams last year, and there was a contractor in the audience, and he looked at me. He just said, you know, the same question was asked, and I gave the same answer. And his response was, "I'm a contractor. I can tell you that's cheaper than putting a slab on top." So that's the best information I have today.
Okay. How are these pre-stressed concrete beams anticipated to perform in earthquake?
Yeah, good question. Again, we're emulating a slab bridge. If you have slab bridges in your state, the behavior would be the same. The question is, you know, how do you keep the bridge from moving around? Typically, what we see being done is either the back wall of the bridge will anchor the bridge for longitudinal seismic forces and transverse seismic forces. Most states put a keyway block on the outside corners at the ends of the bridge. So there's different details out there in different states. They all would work here. So however you would detail a slab bridge, the same details would work here. We do not recommend putting pins at the end of the bridge. Running a pin through the end block of a bridge, it can be done. It typically takes out 4 strand in your cross section. So because usually have a fairly large hole that you drop a dowel in. You can do that. If your state does that for seismic, that's fine too. I don't recommend it because you typically lose 4 strand with that detail, and that's just shortening your maximum span lengths. But whatever details you use for box beam bridges would work here as well.
Okay. The question was, what options are available when the deck needs replacing?
There's no deck on the bridge. There's no deck on the bridge. You could patch the top of these beams like you would any deck in theory. Our history is pretty good on these things. They hold up pretty well if you have them protected properly with some type of overlay, either concrete or asphalt with membrane.
Okay. Prior issues been due to over sealing the keyway bottom, resulting in grout not engaging the lower shear key slopes at all?
Yeah, interesting question. Interesting question. We had a bridge years ago in Connecticut where the shear keys failed. I mean, we call it piano action, the piano key. The beams were deflected independently. The shear keys were completely shot. And we took cores through the shear keys to see what was going on. And kind of the exact opposite was the issue. We took a core through a failed key and the key was gone. It was just pulverized. We took a core through one that was cracked. And what did we see was the top half of the shear key there were voids. When they poured the grout in the shear key, it filled the bottom of the key, but they didn't quite get it all the way to the top. And we think that might have been a failure that led to this differential. So that's why we're kind of getting away from these keys. The workmanship can really play a significant factor in the durability of those bridges with the just grouted keys. We're trying to go to a more robust reinforced concrete connection, which is easy to get the concrete in the hole and fill the entire shear key. And then on top of that, we have the reinforcing every 6 inches.
Okay, and then how do the precasters maintain the integrity of the void form alignment, and how do inspectors verify the alignment?
I love that question. One of the reasons we're proposing not to use voids in the solid slabs is for that exact reason. It's a pain in the neck to put a void inside of a box beam. They know how to do it. They have done it. You have to anchor it down properly because it will float. Those voids used to be, years ago, were made with cardboard, wax impregnated cardboard. Nowadays is expanded polystyrene, which obviously floats. So you have to anchor the thing down and have it usually anchored to reinforcing or the strand. Fabricators know how to do it. As far as verifying it, unless you cut the beam in half, you don't know exactly where it is. So there have always been concerns with that. But you know, there are ways. I guess in theory, a pulse echo device could tell you where the void is. Or GPR maybe, but the reality is they follow standard practices in the fabrication shop. They know how to anchor these things and keep them from shifting in the forms. So it's something that we've been doing for 50 years. They know how to do it, and we'll continue to do it for these deeper sections.
Okay. How do you ensure correct rideability and drainage that results from the beam camber if it doesn't have a deck?
Yeah, like I mentioned before, we typically run the beams on the cross slope, so they're in the cross sections and the details show that. As far as camber, I talked about that quite a bit. It's something that I have an entire presentation on how to manage camber and profile to get the right weight profile, and the 2 options are vary the depth of the beam. It's one option. And the second option is vary the thickness of the overlay if you have an overlay. So if you want to go with a bare concrete deck, you pretty much have to vary the thickness of the beam over the length of the bridge. And we have notes and details for that. It does add cost to the beams, so it's something you got to keep in mind. But you can go, we try to give as many options as possible. The owners can choose whatever works best for them.
Okay, I'm going to let Jamal come on and ask some questions. We have a whole lot more questions here.
Thank you, Paul. Mike, a great presentation. There's some questions that came in during the presentation. The
Yep.
first one, how do you form the closure over a waterway?
Yeah, if you looked at the photos in the presentation, and you can go back and look at the copy of the presentation and see, the contractor in Vermont, what they did was they had vertical rods going through the closure joint, and they formed it up from the bottom. You still have to get under the bridge to strip the forms. You're gonna have to get underneath there and take the forms off. I know Mass DOT is looking for a detail where they're gonna perhaps allow inserts in the beams to bolt the form on the underside of the beam. There's several different options out there, but it's gonna require, removing that form is gonna require getting under the bridge after you cast the joint.
Great.
Mm-hmm.
Another question, what kind of rebar are you using in the shear key? The photo looked like epoxy coated rebar has been used.
Yeah, a lot of states still use epoxy coated bars. That's Vermont, that photo was taken. They use epoxy bars. Any bar can be used. We're seeing states moving more towards galvanized bars and some of these corrosion resistant bars that are out there as well. So basically, and whatever you're using for reinforcing in your decks, I would recommend using that same reinforcing for that joint.
There's a question about phasing, Mike. How does phasing impact the use of these deck panels?
Yeah, we're designing, as I mentioned in the presentation, my firm is designing a phased construction project now in Pittsfield, Massachusetts. The key thing is you have to make sure the phase joint, the joint between phases, has to be wide enough so the hook bars can fit in there. So you can erect that beam, and then when you go to the next phase, you can lap the next beam over. I mean, rule of thumb is you want to have that phasing joint probably about 2 feet wide anyway. When you look at things like earth support, like sheeting off the behind the abutment, you don't want to keep that phase line too tight. It runs into a lot of problems in construction. So you just have to make sure you have enough gap between the first phase and the second phase so the hook bars can fit. Aside from that, there's no other major change.
All right. This is from MassDOT. You mentioned Alex Bardot is a member of the committee. They say
Yes.
they do not use a lot of pre-stressed concrete in Massachusetts, and they use next beam. Are you aware that these details are included in the MassDOT bridge manual?
Wow, that's a great question. Who asked that question? I'm curious, but I can answer for that. The answer is
Christine McLaughlin.
Yeah, okay, that's great. No, the answer is, as I mentioned, we're publishing these details this week, and we had a meeting last month where we finally approved these details, and we're going to publish them. And as I mentioned, Alex is a member of the committee. After the meeting, Alex pulled me aside and said, "Okay, now we got to put it in the bridge manual, because we approved it." So actually, my firm works with Alex and his staff and another engineer named Joe Gill, who's the former state bridge engineer. We help Alex work on his bridge manual, and as we speak, details are being developed right now to be included in the Mass DOT Bridge Manual in an upcoming revision. So it will be in the Mass DOT Bridge Manual.
That's great, and they have a great manual, by the way. There's a question about the spreadsheets, if they're available to the public. You mentioned that.
They will be, yeah. They may not be posted yet, but they will be.
Okay. Have the committee considered the use of links spans across the bridge at the end of the precast beams?
Yeah, the answer is whatever details you use for link slabs on like any other bridge, we haven't developed details, but I can't see any reason why you could not use. What I would recommend, New York State DOT, and I think we had an FIU webinar on the subject, UHPC link slabs in New York, I think are excellent details and would be very much applicable to these beams. You'd have say a 6-inch notch in the end of the beam, and you pour a small UHPC joint at the end. It's an excellent detail, and it would definitely be applicable to these as well.
Another question about the pier, the continuity over the pier of the deck. Any details that you have regarding the details over the pier?
Yeah, the same detail you would use for a Jason box beam or a solid slab or a deck slab pre-stressed bridge would be applicable here. I know Mass DOT has details for continuity connections at piers. Many states have details for continuity connections for box beam bridges at piers. And there are quite a few different details. There's different ways of approaching that with bent up strand coming out the end of the beam, and there's a lot of dimensional requirements, and then having a block out on the top. So it can be done. What I suggest is do a little bit of research on what states are doing for continuity for box beam bridges, and they would be applicable to these bridges as well.
All right. Question about shrinkage and creep rates will be different between the pre-stressed beams and the cast-in-place connection. That could lead to tendency for longitudinal cracking. Has this been observed?
We don't see that as an issue. The closure joint between the beams is very similar to a composite deck cast on top. So all very commonly take a pre-stressed girder like a bulb T and cast a deck on top, and you have differential shrinkage and differential creep between the two. And the same issue with these keys, but these keys are so robust and so strong, we don't see that being an issue at all. If you want, you could calculate that differential just like we do with composite deck toppings, but the amount of reinforcing we have in these joints is significant, and we don't see that as being a problem, and it hasn't manifested itself as problems in the bridges that have been built to date. So it's an interesting topic, but reality is we make composite connections to pre-stressed beams on a regular basis. The key thing to understand is most of the creep occurs before the pour is made. And the reality is, and I know Reed Casterdale, a good friend of mine, he has mentioned before, that once you cast topping on a bridge, the creep stops because it's just the beam can't creep anymore because the composite concrete you cast against it is restraining it. So it is an interesting subject, but we don't see that as being a major problem.
Oh, good. This is a long question, Mike. It deals with the reinforcements, longitudinal reinforcements of the closure pour. It says, how is the level of longitudinal reinforcement at the bottom of the closure pour determined? The bottom of the closure pour will be subject to tension due to longitudinal bending and do not contain the same level of primary reinforcement as the beam. A big difference between the next beam connection and the connection for the deck slab is that the nuclear, the NA, is within the depth of the connection.
Neutral axis, yeah, I understand. You could, if you're concerned about that. We were not concerned about it as a committee. The live load stresses are not that high, but we barely will see cracking of that concrete due to tension. But if you are concerned with it, you can add more longitudinal bars if you want. If you want to add larger bars in the bottom to control that cracking, that potentially might happen. The key is you may want to do calculations to see what is the service level stresses in the bottom of that concrete pour under live load. I imagine they're not all that high, but if they are, you can add reinforcing to control the cracking in the bottom. There's room to add bars down there if you desire. Good question, real good question.
It is a good question. And that's the last question I have here. There's one more that came in right now. Can you please elaborate about the poured concrete in the joints? And I think they're looking to see what kind of concrete that you're going to be using in the closure pour.
Yeah, good question. There's another thing I want to add too. We recommend whatever concrete you use for decks in your state should be the concrete you use. You can use UHPC, but again, it's a lot of UHPC and it's expensive. So you can use one or the other. One thing I forgot to mention is for the design of these beams, we are recommending ignoring the structural stiffness of that closure pour concrete in the design of the beam. It's conservative. We're assuming the bars in those closure pours are doing nothing, just connecting beams. We treat it as the dead weight. We take into account the dead weight in our dead load calculations, but we ignore the stiffness and strength of that concrete. So we're taking a conservative approach. But as far as the actual concrete itself, we do recommend you want a durable concrete. So you want something that you would typically use for a bridge deck would be the concrete that would be applicable.
There's a question about serviceability, how you check for these joints.
Yeah, like I said before, if you're concerned with serviceability with crack control in the bottom of the joint, you can run calculations using standard AASHTO equations and perhaps add some more steel in the bottom of the joint to control the crack. And the key thing about serviceability, first you have to crack the concrete. So you have to go essentially above the modulus of rupture of that concrete. to even have a crack start. And keep in mind, the only stresses on that closure joint are composite dead load and live load. And in most cases, it's not very high. But if it is high enough to go beyond modular rupture, then we add reinforcing to control the width of the crack. But one thing I like to say is, we put the steel in for serviceability, and we say it's not called crack prevention reinforcement, it's called crack control reinforcement. If you exceed the modular rupture for that concrete, it's going to crack, and your reinforcing then is there to control the width of the crack. Now, keep in mind also, a crack on the bottom, a minor crack on the bottom of this closure joint is not really going to affect the durability of the bridge because very much because it's not exposed to the severe exposure the top of the deck sees. And we're not going to see cracks in the top. We might get some minor shrinkage cracks, but again, if you want to really control that, add reinforcing, longitudinal reinforcing to that joint to control the width of the crack. Not to eliminate the width of the crack. That's the key. It controls the width of the crack. Interesting to the point. This is a really good subject that you might say, I got to snake those bars through all those hooks to get them in there, but there's actually ample room below the bar and above the bar. If you notice, it's like 3 inches up. You can actually tie those longitudinal bars to the underside of the hooks pretty easily if you wanted to. It doesn't have to be within the hook. It could be below the hook as well.
There's another question regarding the cracks again. If there's no overlay, do you seal the longitudinal joint between the precast and the closure pour?
Yeah, there was research done at Federal Highway looking at leakage through joints in prefabricated deck panels years ago, and that's where this concept of using exposed aggregate was recommended to control, to get a better bond of the concrete in the closure joint against the precast element. What Federal Highway found, and New York State, I looked at a bunch of decks too, they found by going to exposed aggregate that the leakage, the potential for leakage of the joint was dramatically reduced. So if you were to get a shrinkage crack in that closure joint, there are methods for sealing that crack. There's methacrylates that can be used to seal it, but we recommend the exposed aggregate. And a key thing about the exposed aggregate, I say this every time I give presentations, exposed aggregate and 1/4 inch amplitude are two completely different things. In the ABC guide spec, the AASHTO ABC guide spec, we define exposed aggregate as you can see the aggregate, but we don't need 1/4 inch amplitude. The 1/4 inch amplitude comes from AASHTO provisions for composite decks on top of bolt T girders, where you're looking to get horizontal shear transfer, and you want to use that shear friction calculation using a certain cohesion factor and a friction factor. That's 1/4 inch amplitude. For these joints, we just have to expose the aggregate, and we have found that dramatically improves performance of the joint. I gave a presentation, I think I did an FIU presentation on performance of deck level connections. And I gave one example was the Fast 14 project in Medford, Mass. Bridges have been in service for 13 years, and there's no leakage through the joints at all. So it does work if you do it right. Again, I'm a big fan of waterproofing membranes and overlays. We've had very good performance with those. But every state does stage construction. Whatever you do at a stage construction joint, this is the same thing. We just have more joints. So it's really the same.
Perfect. And Mike, that was in November of 2024. So if anybody would like to dig up that presentation from the archives, it is available. Speaking
Excellent.
of which, there were a couple of questions on the availability of the documents from this website and also recording. So I just wanted to remind everybody that the archives do exist in the IBT ABC UTC website. You can go there and find archives of all the presentations we've done. We usually have those up within 48 hours.
Say one more quick thing, just like, again, I want to thank the committee who helped develop these things. I push the mouse, but the committee makes a lot of the decisions. Sarah Patry is our executive director who runs the committee. And some of you may know Rita Saradarian. Rita has retired and Sarah has taken her spot. Rita had a lot to do with this as well. So I give credit where credit's due. It's a committee operation, and it's called the Northeast Bridge Tech Committee, which is New England and New York State are members of this committee. So give credit to that group.
Perfect. Well, thank you very much. And Mike, thank you so much for sharing your time and expertise with us today. With that, our presentation is complete.